Welcome, and today we're going to start our next unit, which is all about inference, primarily dealing with proportions. But for today, we are going to be talking about estimation and margin of error, interpreting a confidence interval, and sample size and confidence level. So careful, there's two things beginning with confidence here. We want to keep them clear. So we're using some material that has to do with Hurricane Katrina. Hopefully, you've all heard about Katrina, even if you were not there or were infants, you don't remember it. But during Hurricane Katrina, New Orleans was flooded, and people tried to find anywhere they could that was elevated. Well, the Superdome, almost said Alamo Dome, the Superdome is elevated. I don't know if you can see right here. This is the bottom platform that the Superdome sits on. So this was a relatively safe spot. And so hundreds, thousands of people made their way to the Superdome. Here you can see a little image of all the people that are in here. Well, we need to figure out how much aid we need to get in here because New Orleans was flooded for days, even weeks. And we needed to find a way to take care of all these people as a society. So FEMA was tasked with trying to estimate how many supplies, beds, food, etc., that they needed to bring in to take care of these people. It's impossible to count every person, or it's not effective. It takes too long to do that. People will have needed some medicines before we could count all of them. So they have to make an estimate. And we want to look at how do they make this estimate. If they underestimate, they're not going to have enough resources to take care of the people. If they overestimate, well, some of the people in other areas outside of New Orleans will not have resources because those resources will be redirected into New Orleans to the Superdome. So we've got to figure out how we go about this. So we are going to do a cluster random sample. And if you remember back, a cluster sample is you've divided up your population and you're going to pick several clusters and then measure everything within that cluster. So some advantages are it's unbiased, especially if the sections that we're going to use are equal size. And it saves time, so we don't have to count everyone. And because we're going to use sections, the Superdome is already divided into sections like any arena is. So we already have these natural divisions, so it'd be easy to figure out which ones to count. So we're taking a random sample of clusters. So we pick 10 clusters or 10 sections that we are going to measure and count how many people are in there. Okay, so we go ahead and we sample these sections. And here are the 10 sections and how many people are in each of these 10 sections. And we want to, based on these, calculate an average number of people per section. So if we add these all up, divide by 10, we get there is an average or a mean number of people per section of 137.7. And that symbol we use is X bar because this is numerical data. It's quantitative. There are a total of 120 sections within the stadium. So my estimate of the number of people in this stadium is 137.7 times the number of sections, which gives 16,524. So that is my estimate of the number of people who are in the Superdome that we need to take care of. Is it perfect? Absolutely not. Absolutely not. So even though our estimators should be unbiased, there is chance variation that occurs. We may overestimate the population or underestimate it. Okay, so we have got this estimate right here. This is a point estimate. But we have to then decide how are we going to figure this out. So, there we go. So our confidence interval is defined as the point estimate plus or minus some margin of error. So let's just see right here. Here, my point estimate was 16,524 people. And then maybe to give some margin of error. I might say plus 3,000 or less 3,000 people. So my lower value in the confidence interval is 13,524. The upper value is the 16,000 plus 3,000, so 19,524. So I have this interval. My confidence interval goes from 13,524 up to 19,524. Okay, so that is my confidence interval. But where did I come up with this 3,000? Why 3,000? What if I want slightly different numbers? What if I say instead of 3,000 as a margin of error, I want 300 as a margin of error? So in that case, I still have the same point estimate. I'm only adding 300 and subtracting 300 from that point estimate. So my confidence interval now goes from 16,224 to 16,834. Well, that seems much more exact, doesn't it? So it's a much narrower interval. So narrower intervals are more precise, but they make you less confident that we've captured the true parameter value. And in this case, it's a mean that we're looking for. So we are not as confident that we've captured the true number of people in this interval because it's much smaller. Okay, well, what if I said, okay, well, I think it's important that I capture the true number of people in the Superdome. So let's make this interval wider. So by making my margin of error smaller, it made the interval smaller, but I was less confident. So if I want to be more confident, I need to make this interval bigger. So let's see. Let's, instead of having 3,000 as my margin of error, let's make it 16,000. That's really big, isn't it? So my point estimate minus 16,000 and plus 16,000 gives me an interval that goes from 524 all the way up to 32,524. Well, that's a pretty darn big interval. I'm pretty sure I've got the true number of people in the Superdome in this interval. So wider intervals give us more confidence that we've captured the true parameter, but they're often not as useful. How would you plan if someone told you, well, there's between 524 and 32,000 people? That would make planning very difficult. You're pretty confident, though, that the true number is between these two values, but it makes planning very, very difficult. So it's not very useful to have this super wide interval. Okay, so let's talk about how to construct and interpret a confidence interval. So the mean from my samples, from those 10 sections that I sampled, was 138. I rounded it to the nearest whole number here. So that's the mean number of people per section based on the 10 sections we sampled. So I'm going to put 138 here. That's my point estimate. But how far out should I go? How far do I want to say is my margin of error for this? So let's think back to that 68, 95, 99.7 rule. And if you remember, 68 represented that 68% of our values are found within one standard deviation of the mean. So the the mean minus one standard deviation and the mean plus one standard deviation. That gave us 68% of our values. 95% represents if I went two standard deviations above the mean and two standard deviations below the mean. And right here, I was told that the standard deviation of this is 3. So in the beginning, to get the 68% of my values, I would have 138 plus 3 and 138 minus 3. So that defines the limit or the boundaries of where I would find 68% of my data. If I wanted to go 2 standard deviations away from the mean, I would go 2 times 3. So 6 units below, 6 units above. And I should capture 95% of my data. If I wanted to capture 99.7% of my data, I would go 3 standard deviations above the mean and 3 standard deviations below the mean. Okay, so again, the 6 to 8% is if all possible sample means are within 68% of them are within 1 standard deviation of the true mean. 95% of the sample means are within 2 standard deviations of the mean. And of course, if we went to 3 standard deviations, we would get 99.7. So let's take a look and decide how much is enough here. So we want to construct a 95% confidence interval. So first, we need to figure out what we're really trying to do is find out what is mu for the population. So how many people are in the Superdome? I've got my sample mean from those 10 sections we took. And I've got to decide, I know the standard deviation is 3. Do I want to go 2 standard deviations away? And the way, again, we did this is if the standard deviation is 3, and I want to go 2 standard deviations away from that, I would say the interval is going to be defined as the mean minus 2 times the width of the standard deviation, and 138 plus 2 standard deviations away. And again, the 3 is the width of a standard deviation. It's 3 units. So these values, 138 minus 6 gives me 132. 138 plus 2 standard deviations is 144. So this is my confidence interval right here, 132 to 144. Now we need to know, how do we interpret this? So there is a way we will interpret this. And this, make sure you write this down and highlight it. This is something you will use over and over again going forward. So the way we interpret a confidence interval is we say we are whatever the confidence interval percentage is. So in this case, it's 95. So we are 95% confident that the interval from the lower value to the upper value captures, keyword again, captures the true parameter of context. And in this case, the parameter we're dealing with is the mean. So it captures the true mean number of people per section. That's the context of this problem. So again, confidence intervals will always be interpreted by saying we are blank percent confident that the interval from the lower value to the upper value captures the true parameter of, and then what the context is. And we can't just say parameter, we have to either use mean or proportion, depending on what you're looking at. Okay, I'm going to tell you the wrong way to interpret this, just because inevitably someone will do it. And I want to make sure we get clear this is not true. So the wrong interpretation is to say there's a 95% probability that the interval from the lower value to the upper value captures the true mean number of people per section. It is not a probability, because that true mean number of people per section is already a given. It exists. So either it's in the interval, in that case it's 100% probability, or it's not in the interval, which is a 0% probability. Okay, so what we're saying is that we are 95% confident that the interval captures it, not that there's a probability. I know that's a kind of subtlety, but just remember, we don't talk about probability with confidence intervals. Okay, and so here's my picture. If this is the true mean number of people per section, if in this 95% confidence interval, in this case, it is in the interval, so the probability is 100%. In this image of it, if the true mean was over here, it's outside the interval from 132 to 144. So there is a probability of it being in there is 0. It's not in there. Okay, so again, the parameter has a fixed value. And again, here's how we interpret a confidence interval. We are 95% confident that we captured the true mean. Okay. Even though our interval already captured or did not capture the true value, we don't know whether it did or not because we don't know the true mean. So we can only be a certain level of confident in terms of if we captured it or not. Let's turn over. Okay, and the last thing we want to talk about today is interpreting a confidence level. Okay, so level, not interval, but a level. So let's take a look at what we had already looked at. So here was my point estimate. And because we're doing a 95% confidence interval, that means I'm going 2 standard deviations above the statistic and 2 standard deviations below the statistic. Because again, remember, the statistic comes from your sample. And my sample size was 20. So let's say that we sampled 20 different sections there. Okay, if I wanted to increase my confidence level, so if I want to go up to 99.7, I need to go out 3 standard deviations. So notice this is a little wider. This is the same scale here. So I've kept the same sample size, but I increased my confidence level because I went out 3 standard deviations instead of 2. And so what we need to say is that if you raise the confidence level, the confidence interval becomes wider. Because to get that higher confidence level, we have to go out further, more standard deviations. So when we have this wider confidence interval, we have a higher confidence of capturing the true value, but the interval is less precise. So it's a much bigger interval. So in terms of planning for supplies, I think I would prefer a smaller interval versus a large interval, even though this might capture, this is a better chance of capturing the true mean of the population. Okay, what if we kept the 95% confidence and we changed our sample size? What impact would that have? So let's take a look here. So here is the same scale, but the 95% confidence level now is going to be much closer because we're looking at 2 standard deviations, because when the sample size increases, the standard deviation gets smaller. So even though I'm still 2 standard deviations away, the standard deviation itself for the sampling distribution has gotten smaller. And we should remember that from our last unit. When we increased our sample size, the data got pushed together, the sampling distribution. And that's because the standard deviation was divided by the square root of n. Okay, so if you raise the sample size, the confidence interval becomes narrower, so we have a more precise interval even at the same confidence level. So it's more precise. And if we're looking to increase our precision, the way we do that is increasing the sample size. And let's take a look at one last thing, and then you will be done with this and ready for the homework. So there is a link right here. If you want to go into this applet, it will help you graph a population distribution and then a sampling distribution. So the way we interpret this, each one of these was the result of one sample. The dot represents the mean of that sample, and mu is the true mean of the population. So you can see how many of these bars or these confidence intervals are captured, are that they captured the true mean. So all of these have the true mean inside the interval, except for this guy. Because that bar doesn't overlap with the mean value, it did not capture the true mean. But all the rest of these did capture it. So what this is saying is that if we took many, many, many samples of the same size from the population, about 95% of those samples will result in an interval that captures the actual parameter value. In this case, it's a mean. Okay, so again, the idea here is if we took many, many samples and each sample had the same number in it, that we are 95% confident that the interval will capture the actual true parameter. And this is just a visual showing you all the different samples and how many of them actually capture this mean value. Okay, something for you to think about. So here is a 68% confidence interval, the 95% confidence interval, and the 99.7 confidence interval for the number of people in the Superdome. And again, the point estimate was 16,524. So if you have to talk to FEMA and make an interval or report to them, which one would you use? And how would you explain to FEMA what the interval means? And what would you recommend they do with it? So just something to think about. You've got this.